Hello everyone. Myself Pradeep Kumar Vai, Assistant Professor, Department of ECE, ATM College of Engineering, Mysuru. In this video, let us see an experiment called Off Adder. So by using Verilog language, how to develop the Verilog code for half adder that can be seen through this video. The very objective of this experiment is to understand and appreciate the one of potential characteristic of Verilog language. That is, it is the Verilog language is so flexible that the designer need not to know complete information about its design entity. Rather, if the designer knows only any one kind of an information, that itself is sufficient. So the Verilog provides you an opportunity to develop the device which is intended. So that can be understand and that can be realized through this experiment. Let us consider our design interest half adder. So you know that half adder is a combination logic circuit which essentially consists of two inputs and two output. So in this particular slide, I had shown half adder block which consists of two inputs. I named it as A and B, and two outputs. I named it as sum and carry. So the function of this half adder is expressed through truth table. It is a device which adds to one bit number and produces the sum, and also which produces the carry. So if the inputs A and B both are 0 0, essentially the sum is 0 and carry is also 0. If any one of the input, either A or B, is 1, then sum will be 1, which yields no carry, that is, carry is equals to 0. And if both inputs are 1 1, then sum is 0, which produces the carry bit as 1. So this is the functional function of half adder. Now, through this slide, we have understood the one dimension or one information about the half adder through truth table. So if you have the truth table or functional table of any digital device, then also by using this functional table, we can develop the Verilog code. Popularly, we know that method the approach is behavioral description. Or else, by looking into the truth table, we can write the some more information, that is the Boolean expression corresponding to the half adder, can be written as sum is equals to ax or b, and as well as the Boolean expression for the carry output is can be obtained as carry is equals to a and b. And often this Boolean expression can also be expressed in terms of interconnection of the logic gate. So this particular diagram shows the logic diagram of half adder, which consists of A, B, which pass through over the XOR gate. The output of the XOR gate is referred as sum, and the inputs A, B by passing over the AND gate, the output will be referred as carry. So for half adder, we are going to recognize it, recognize the function of the half adder in either three methods. The one is either through functional table or truth table, or through Boolean expression, or even through interconnection of the logic gates. Okay, so the Verilog for to develop the half adder in Verilog, either if you know the truth table and if you are not aware about the Boolean expression or interconnection of the logic gate, then also Verilog provides an opportunity to develop the code. Uh, and as well as if you are not aware about the truth table or interconnection of the logic gates, but you have an information in terms of Boolean expression, then also we can develop the Verilog code, so which will be popularly referred as data flow description. Or else, if you have a ready information about the digital device what you want to design in terms of interconnection of the logic gates, then also even without knowing or without having the knowledge of the functional table and the Boolean expression, by looking into the interconnection of the logic gates, also we can develop the Verilog code. So this is the one of the potential characteristic of Verilog code. So that we're going to look means we are trying to develop the Verilog code for the half adder, both in data flow description, behavioral description, as well as in gate level description. Now let us consider the data flow description, where for data flow description, popular basically we will be using the Boolean expressions. Okay, and we have to establish the relation between the inputs and output through Boolean equations. So that approach referred as data flow description. Whether it is a data flow description, behavioral description, or gate level description, the module part will be remain same. Only the body of the Verilog program, the approach of writing the interconnection between the inputs and output, or establishing the relation between the input and output of the device will be changing, whereas the module part will be remains unchanged. So let us go with the Verilog code. First, we have to declare the module part. So here we have declared the module with a keyword called as module, and followed by the name of the module. I refer it as half adder. It is a user defined name. And next, we have to list all the ports which corresponds to the device, corresponds to the design. So this design entity requires two inputs and two output. So all the ports, irrespective of whether it is an input or output, that has to be listed within the parentheses. This is very essential uh, part while writing the Verilog code. Next, let us describe the directions of the ports listed in the very first line. So, in the very first line, we have listed sum and carry, A and B are the ports. Out of four ports, sum and carry are referred as output direction or output port, whereas A and B referred as input port. The directions of the port has to be specified through the keyword output and input. Directly, we will try to establish the relation between the input and output through data flow statement. So wherever we are using a keyword referred as assign, so this is the keyword in the Verilog. So this assign keyword indicates the statement what you have written will be under the consideration of data flow statement. Okay, so assign is the keyword which calculates the LHS part, and the calculated result will be assigned to the RHS. Essentially, RHS should be of the type of output, and whereas LHS should be of the type of output, whereas RHS should be of the type input. Okay. So assign the relation between A and B and sum is equals to A XOR B. So this cap indicates XOR logical operation, and whereas carry is equals to A and B. Okay, where ampersand indicates logical and operation. So the logical expression of the design entity is expressed directly in the form of data flow statement in the Verilog code. Okay. At last, we can end this module with the keyword end module. So this is the one way of writing the Verilog code for half adder. So this statement is referred as data flow statement. Now we will write a test bench for half adder. So test bench is the again Verilog module. So which generates the necessary inputs for the design under verification. Or here in case this it generate the inputs for half adder, and the response will be recorded. Okay. So the stimulus block, let us consider the stimulus block as a main module in this approach. This stimulus block will be referred as main module. And in this stimulus block, since my design block consists of two inputs and two output, I required the corresponding registers and wires. So in the main block or in the main module, that is in the stimulus module, I declare A and B. Okay, these are all the two register type of variable, so that which can hold the signals for input A and B port. Similarly, I declare two more uh, variables called S and C. This should be essentially of the type wire. The sum will be connected to S and carry will be connected to C, so that the response which is generated by the off adder will be recorded through S and C. And we have to instantiate, we have to call a copy of the off adder, and we should establish the connection between A of main module with the port input port A of the off adder. Likewise, B of the main module should be connected to port B of the off adder, followed by sum should be connected to S and carry should be connected to C. and then the necessary signal will be generated to the half adder and the output will be recorded. Okay, so part of that we will declare the stimulus block with the name referred as main. So main is the module name of the stimulus block. Essentially the test bench should not consist any ports which is not synthesizable. And then, as I told, we require two variables of wire type which is supposed to connect it to outputs. So here we have declared it as sum, that is S and C, whereas two more variables which is to hold the value for the input which is of register type, which is declared as A and B. So keep remember, if you want to connect any variable to the input ports in the test bench, you have to declare them as registers. Whereas if you want to connect any output ports in the to the in the stimulus block or in the test bench, that has to be declared as wire type. This is the port connection rules. Okay, the compatibility rules of port interconnection. Now, the very important step where we have to instantiate the design under verification. So our design under verification is off adder. So we have instantiating that off adder through the module name, and HA is the instance name. Okay, this is the instance name, which can be any user defined name, whereas the design under verification should be called in the proper module name. Okay, where we have established interconnection between the ports of the half adder with the variables or of a test bench through connection list. Okay, so here dot a, within this parenthesis I have connected a, which means the input port a of the half adder is connected to the variable a, this register a in the stimulus block, and the next connection should be separated by comma, then the dot b, that is the input port B of the half adder is getting connected with the B of stimulus block, then separate with comma, then the output port sum is connected with the S of the test bench, and at last the output port carry is getting connected with, that is dot carry getting connected with C of the stimulus block. So this is the process where we have instantiated the design block, and we have made an interconnection between the registers of that stimulus block with a register or wire of the stimulus block with the design under verification. Next, we will write generate to generate the necessary control signal. We will write the corresponding combination that has to be encapsulated within begin and end in the initial block. So in the initial block, we are writing the various combinations for input A and B. So at the beginning, we are making A value is equals to 0 and B value is equals to 0. But after 10 times of simulation time, we are making A value as 0 whereas B value as 1, and then after delay of 10 time units, means at the 20th time unit we are changing the value of a as 1 with b is equals to 0. Similarly, after 30th unit of time, that means after 10 units of time delay of the previous execution, we are changing the a and b value as 1 and 1, and at last we are ending those combinations. Okay, this is a user defined combination. The developer, if you want, you can feed some more combinations, since which covers all the four possible combination, which is sufficient. If the combinations are more, only sample combinations can be included in the control signal part. Okay, and since I have multiple statement in the initial block, it has to be encapsulated between begin and end. At last we will write the monitor statement, which is a system task, so which monitors the changes happened in the specified signal. If any changes happened or observed, the monitor statement will be printed. Okay, so this is just similar to printf statement in the C language. So dollar, it is the system task indicator, any keyword which is predefined with the dollar symbol, which is referred as a system task. So dollar monitor, so dollar time, this is a system task which prints the current simulation time, and any printable statement that should be encapsulated within two quotes. So where I have written a equals, b equals, with three dash, and then sum equals and carry equals, and where a will be printed with the binary value, and B also displaying with print binary value. All the variables what I have listed here is going to be displayed in binary value. So backslash n indicates it is a new line character. Then after closing the printable statement, the corresponding variables must be listed here. So a comma b comma s comma c, where a corresponds to first binary value, which is written as a equals, whereas the value of the b signal will be located in this position, whereas the value of the signal s will be located in some position, and the value of the signal c is located in carry position. Okay. At last, the test bench can be ended with end module statement. Okay, so this is the test bench for to test the operation or functionality of the half adder, and the test bench remains same whether you have written the Verilog code in uh, data flow statement or behavioral statement, or else in the gate level statement. Essentially, the test bench, same test bench can be used to test the functionality of the digital device. Okay, that is functional, in this case, functionality of the half adder. Very important, you should observe that the corresponding display variable should be matched with the signal what you have listed in the monitor statement. Okay. Now let us simulate the same in the online simulator, Verilog online simulator. So I'll take the copy of this is the online simulator, online Verilog compiler, as described in the previous video. So where this provides an opportunity to compile and as well as to simulate the design